各位老师、各位同学，我们很高兴也请到了淡江大学的吴俊毅教授。那吴教授的话是在2015年在德国的杜塞道夫大学拿到他的博士学位，然后之后在日本的广岛大学以及日本的东京大学做博士后研究。那因为研究表现杰出，所以在2021年的时候被淡江大学所网罗，然后到淡江大学物理系。那吴教授他的研究专长的话是关于量子资讯以及量子光学方面的研究。那今天的话，很高兴吴教授要为我们讲他的 detection of multi-particle entanglement in boson sampling systems。那我们欢迎吴教授。
谢谢周老师这样的 nice 的这个 introduction， 尤其是说什么研究表现杰出，我觉得应该有点那个，可能不一定是这样，没关系。总之就是 try my best to do the research。那么，我可能在做演讲的时候，可能会用我比较习惯的用英文来做演讲，所以希望老师同学们能够这个。体谅一下因为我中文可能没有那么好，专业方面的专业用语上面的。Okay, so then please allow me to give the talk in English. So today's title is Detection of Multipartite Entanglement in Boson Sampling System. So actually in this title, you will see there are I think three aspects that we might talk in this speech. One is the multipartite entanglement. Okay, this is a fundamental concept, in the quantum foundation. And then the second is boson sampling system, which is a spatial linear optics network system. And then the third is detection of this multipartite entanglement. So the ordering of this talk will also follow these three aspects. One is we first introduce what is multipartite entanglement, and then we talk about how to what is the photon statistic in boson samplings, what is the spatial properties of quantum multipartite quantum system in boson sampling system, and then in the end we will show you how to detect this multipartite entanglement. So three parts. But before we go into the very fundamental or deep mathematics, let me start with something romantic. So I think 3 days ago is 502 so it's a special day. Okay, I think it's a kind of romantic day, and usually physics is not that romantic, but today I try to start with some romantic quantum story as a quantum proposal. Okay, suppose we have suppose Alice and Bob. So Bob want to do a proposal on the wording, and he prepare the ring. And on a date, when he did the proposal, Alice will have two possible outcomes, right? Two possible reactions. One is yes, and the other is no. Okay, maybe this is the. Let me think about it. But let's assume that Alice have two outcomes, yes and no, and Bob. So if Alice says yes, then Bob will be hard-mated, certainly. Okay, with 100 certainty, Bob will be quite happy. But if Alice said no, then Bob will be heartbroken. So this is somehow a relation, and it's a classical relation. But if you want to put this system in a quantum, we just put cat of the Dirac notation, this cat Dirac notation. So Alice, yes, and Bob Harmeting, they are all so Alice has on Alice system they have two state. One is two possible state. One is yes, one is no. And for Bob, he is either hermetic in a hermetic state and or in a heartbroken state. Okay, so now the question is that you may know that in quantum system, Alice may be in some kind of a yes and no state. Okay, and suppose we have a suppose Alice has yes and no superposition, which is shown in this slide. And the question is that what will the state of Bob be? Okay, what will be the Bob state now after Alice say yes and no? Okay, and for this to think about this question, let's take a look at what is the global state of Alice and Bob. So suppose we have a global quantum state of this system. So after Bob proposed, then these two quantum system may well be in this kind of superposition of two different correlation. One is yes correlated with hermetic state, and one is no correlated with heartbroken. Okay, and in quantum system, a special thing is that we can always put things in superposition. If we put these two correlated states in a quantum superposition, then we will have this kind of state assigned with a probability amplitude, and this probability amplitude indicates the probability of Alice of how possible is Alice to say yes or not. Okay, so this kind of state is actually an entangled state. So what is special for this kind of entangled state? So suppose that Alice has 50% probability say yes and 50% probability say no. Okay, now if we change the basis, Alice basis to yes and no basis, and if we write down the psi AB state in the new basis, and Alice will be in, then the new state will be in a superposition of a two new kind of a correlated state. One is Alice state with yes plus no tensor product with Bob's hermetic plus heartbroken. And the second is Alice yes minus no tensor product Bob being hermetic and minus heartbroken. This is the kind of a new representation of the state in the another basis. So to answer the question in the very beginning, I asked that if Alice is in yes and no state, what will be the motion of what will Bob's motion be? Okay, it will be something like Bob also be in a state of hermetic and heartbroken. Okay, so it's a state of happy and sad. Okay, kind of crazy state. So usually, I know if you are in a date, and you will understand sometimes we are also in happy and sad state. Okay, so yeah, but this is okay. This is the quantum proposal. But before we can talk about this quantum proposal, this love story in a quantum system, actually all of the story start with a cat, and this cat is not the this one Tom. The cat is Schrödinger's cat. So the story started from Schrödinger's cat, and actually, I think most of you are familiar with Schrödinger's cat, and it is a thought experiment proposed by here actually Schrödinger is Austrian. Here I mistyped the nationality. Okay, and so in Schrödinger's thought experiment, he put a cat in a closed box. Well, there is a Poisson, and Hamel, and a photon counter, and photon detector, and atomic radiation. So, as you know, that Schrödinger can be dead and alive, but how can Schrödinger's cat become how to say, in this kind of a dead and alive state? Then we need entanglement. So in his paper in this 1930, I think it's 1930, I didn't remember, 31 or 35, I don't quite remember the exact year, but in this paper, this is first time that we have the word called Verschränkung in German, and if we translate it to English, it is entanglement. Okay, so why do we need entanglement in this system? Because actually, the electron. So you may note that electron, you have different energy level. So the electron in the atom have a different energy level. So the electron may be in the ground state or first excited state, etc. So now if we start if we excited electron into a first excited state energy level, then there will be after sometimes there will be some probability that the electrons decay into the ground energy level, and if it decays to a ground energy, then the ground state, then the atom will emit a photon, which equal to the energy difference between these two energy level, and this is due to the energy conservation. So here, in this this state, which say it also exactly saying this procedure. So at some point, we have a 50% probability that the electron still in the first excited state, this is E2, and while we don't have any photons emitted, tensor vacuum, and plus 50% probability the electron is decayed, and then we emitted one photon with the energy equal to E2 minus E1. So this is a superposition, and if you remember the quantum proposal story, it's quite similar to this superposition of a correlated state, which is entangled state. Okay, this is entangled state, but how in Schrödinger's thought experiment, he set up a very smart causality chain to map this microscopic state to a macroscopic state, which is carried by a cat, a macroscopic object cat, and it looks like this. So through the counter, the photon counter, it will map the existence of the photon to trigger the Hamel and then broken the Poisson, such that this causality will lead to a live case or a dead case. So in the end, we will kind of have a entangled state of a system that we have a electron in the first excited state, tensor plot the cat is alive, plus 50% that well, the electron is decayed and the cat is dead. And now this is the so-called entangled state. So and if you remember, if we change the basis to the E2 plus E1 superposition, then the cat will be in dead and alive superposition. This is how we come into the dead and alive cat in this Schrödinger's cat story. But we will be interested in the entanglement phenomenon in this talk. So not about the cat, but about the entanglement. So Schrödinger after Schrödinger proposed this Schrödinger's cat story, actually Schrödinger he proposed this cat story. Actually, he want to try to show some strangeness of the quantum mechanics that about the probability interpretation of the quantum mechanics, because he want to show if we interpret the wave package, the amplitude of the wave package as the probability amplitude, then you will have some state light alive and dead cat, and this sounds very strange. And Einstein took this idea because Einstein he is really the one who did not like quantum mechanics, and he tried to nail down quantum mechanics very hard. And one day he found, after Schrödinger proposed this entangled state, and Einstein come to an idea that, okay, so how about if we have a continuous variable entangled state, and in this system, if we measure position on one system and measure momentum on the other system, and then we will have okay, this is an EPR paradox, and then we will have if we note the exact position on Alice, and then Alice will immediately know the exact momentum on both sides. So in this case, it shows that and now if the Alice can measure the momentum, then he can also note exactly what is the position on both sides. So through this also kind of thought experiment, which was assumed which have assumption on the completeness of quantum mechanics and the reality of the quantum mechanics, and also the locality of the quantum mechanics. And under these three assumptions, completeness, locality, and realism together, then he has a conclusion. We get to a point of a violation of the uncertainty relation, and he said that because of this violation of uncertainty relation, then one of these three assumptions must be wrong. So completeness or the locality or the realism, one of them must be wrong. Then Einstein want to accept local realism. Then he said, okay, the quantum mechanics must be incomplete. Incomplete means that there must be some hidden variable we don't know. Okay, and therefore together, according to this EPR paradox, Einstein, Podolsky, Rosen, they come to a conclusion that we will need a local variable, local hidden variable model for the quantum mechanics. So at that time, people still only use arguments to debate between these two camps. One is I think majorly Einstein versus Bohr, Max Bohr, but they only use argument but no experiment. So until 1964, Bell he finally find out a way to establish a theory which allowed us to test this local hidden variable model in experiment. This is so-called Bell inequality, and the Bell inequality actually set up a boundary which the boundary which can be tested or characterized in experiment. And if we have the correlation which exceeds this boundary, then we can certainly set the Einstein, Podolsky, and Rosen they are wrong. So then we will So now we have the theory, which allows us to test the EPR theory. And in 1980s, Aspect, French physics, and Granger, they finally implemented the first EPR, the bear test experiment, and they get this non-local hidden variable correlation and show that, okay, the entanglement really exists, and we don't need and even the local hidden variable model cannot be employed to describe the physics, the nature of the physics. So we really need this kind of entanglement, which allows kind of a spooky action. Okay, and but at that time, people still don't really quite understand the difference between entanglement and non-local correlation. Okay. Until 1989, Vellner in his paper finally write down the very rigorous mathematical definition of a separable state, and then people note that okay, so when he write down the definition of a separable state, then he reversely defined entanglement as the state which is non separable, and people find that okay, the set of the separable state is a subset of the state which exhibits local hidden variable model. Okay, so that means finally we have a rigorous mathematical definition of entanglement, and this definition, according to this definition, a separable state. So if we want to understand what is entanglement, first we need to understand what a separable state is. So in Vellner's definition, separable state, to understand separable state, we need to first understand what is a separable state for pure state. So for pure state, the most simple one is a product state like 0 tensor 0, 1 tensor 1. That means that we don't have any correlation between these two kind of states. And now the separable state is then defined as, so here is the definition. So a separable state in Hilbert space is separable if and only if it can express it as a convex combination of product states. So this is a convex combination of a product state, which is a mixture of different product state. And this product state, for this product state, we have no correlation. But of course, if we take as a mixture, it has a classical correlation. But this kind of a convex mixture does not have has only classical correlation, but don't have a quantum correlation. And the state which cannot be written in this expression, then we call it entanglement. So as this, according to this definition, we know the set of separable state is a convex set. In a boundary, it is the product state, and we can't kind of close the boundary, then it will be a convex set of the separable state. And the state outside this convex set is named the entanglement state. So for example, in here we have a pure separable state, 0 tensor 0, 1 tensor 1, and then we have a entanglement state here on the boundary of the whole quantum set of quantum states. So one remark is this geometry is not it's an analogy. It is not really how the states order in a quantum Hilbert space. Okay, and so here, if we take a convex mixture, convex combination between the product state, then it will be certainly a separable state in this convex set. But if we now take if we now take the convex combination between the one of the separable state and with the entanglement state, then we will see that we may have separable state or entangled state, and they may have four intersecting points at the boundary of the separable state. And also, if we can draw a line on this about a tangent line, a hyperplane, which is tangent to this set, convex set, then we can separate this convex set of separable states from part of the entangled state. Okay, so then we will see that on the left-hand side, if the states on the right, on this part, on the red highlighted set, then the state is totally entangled. So the same thing we can also do for the convex combination between the 0, 0 and the bare state. So, and this will allow us to detect entanglement in the experiments. Okay, so actually there are many criterion of entanglement determination, and for example, PPT criterion, positive partial transport criterion, etc. And but it is not that directly. It is not straightforward to map this kind of criterion to an experimental setups that allows us to detect the entanglement. So, so the criterion for entanglement, there are two kinds. One kind is for theoretical study. Okay, we can calculate that, we can analyze it now on our paper. We can derive this criterion theoretically, and the other entanglement criterion is operation. I mean, can be implemented or carried out in the experiments to detect the entanglement, to get the nature of entanglement experiments. The one is for theoretical study to determine, okay, if the given state is entangled or not. But in experiments, we need some data, and some of this kind of entanglement criteria is for experiments, can be used for experiments detection. And today we will look at the this kind of criterion for experiment detection. And one of them is called entanglement witness. And entanglement witness is really like the blue line here. We draw a line which we want to separate the convex set from some entangled states. Okay, and this boundary is really works really like if we play badminton. It's really like we stacked up the boundary for the field, and if the ball is inside the field, then you win. If the ball is outside the wind, then you get penalty. Okay, so what we need is that we need a referee to make the judgment on the entanglement state. So we need a referee to see if this ball is in or outside this boundary, and the entanglement witness is the referee. Okay, so here is a propaganda and the Pingdong's government. Okay, is that if you cross the line, you will get penalty. So I mean, I think this is for the red lamp. So if you red traffic lamp, you should stop not across the line. And if you cross the line, you will get penalty. Then in a quantum, if entanglement witness works in another way, that if you have a line crossing, then you will get entanglement signature. And if we don't cross the line, it doesn't mean separable. We don't know. Okay, if we don't cross the line, it may be entangled, it may be several. But if you cross the line, it is certainly entangled. So how can we detect entanglement in an experiment? We will need to construct an entanglement witness, which works like as a referee, and evaluate it in experiments. Okay, so the introduction is quite long. So now I will come into the content of my research. So basically, we want to find a good way to construct the entanglement witness in the linear optics network system, which is the system where we implement boson sampling. So I will go for it. I think I will. So there will be 3 parts, but maybe I will skip one of them to save the time. So the first part is about entanglement detection in single photon linear optic networks. And the second part is about the special property of the multi-photon linear optic networks. One remark is that for single photon linear optic network, it works like a qubit system, but in multi-photon linear optic networks, the photon statistics, because the photon bunching effect, the whole system is not the very like the simple qubit system. We make some spatial analysis of the photon statistic to get the entanglement signature. And in the end, we will show how to detect or generate and evaluate the material entanglement in this system. So first of all, how to detect, how to construct entanglement witness in a single photon in optics networks. So here we will have maybe we have 3 equations, right? Maybe first let's look at the second equation. So the second equation here, it shows the eigen equation. Here V entanglement is a stabilizer of the target state. Stabilizer means after application action of this operator, the state does not change. Okay, so if we evaluate the expectation value of this VEN in a system, so this is what we have in a third equation. And you know that ideally, so for the ideal entanglement target state VEN, we will have the expectation value equal to 1, right? And now if we calculate the theoretical maximum of this expectation value for separable state, then we will get this line, right? We'll get this line, the red line here, and that means if this expectation value of the VEN greater than this B separable, then we can certainly say that the testing state is entangled. Okay. And the first equation is just the conventional or traditional definition of entanglement witness, because at the beginning, when people introduce this entanglement witness, they use another direction. They use minus VEN. So, but actually they works quite similar for this VEN WEN. If the WEN expectation value is smaller than 0, then the entanglement is detected. Okay, so but it works quite similar. So therefore we will use this VEN as our entanglement witness. And yeah, here is the ideal case. We will have expectation value for phi psi En equal to 1. So here, this is for bipartite system, but for multipartite system, then we will need to consider then the situation will become more complicated. We will have A versus BC, or B versus AC, or A versus BC. We will have different possible combination. And state is called biproducible, or yeah, some people will say separable, but more strict speaking, we should say it is biproducible. A biproducible state is a convex combination of biseparable state A versus BC, and biseparable state B versus AC, and biseparable state AB versus C. So if a state cannot be written in this reproducible mixture, then it is genuinely multipartite entanglement. This is definition of a genuine multipartite entanglement. So if we have a target state psi G M E, then we can also construct you may ignore the first equation. Let's just focus the second and the third equation here, and we will also find a state variable VGEN, which stabilize the target state, and we can evaluate the maximum of the maximum value of this separable of maximum expectation value of this V operator for a separate producible state, such that we will get the boundary of this B by producible. And once we get this expectation value of the V larger, greater than this B by producible, then we can conclude the genuine multipartite entanglement of this the testing state. So let me see. We just have the 10-minute step. So here is that maybe okay. I think okay. Let me focus on the first part. Okay. So here is an example. How do we construct a state variable and to detect entanglement in a bipartite system? For example, if we have a psi AB, when we want to determine or we want to, so this psi AB is this psi AB is a target entanglement state, and if we are given a testing state which is a rho AB, we want to test the entanglement, then we will need to construct a state variable that verify or stabilize this target state. And how to construct this kind of state variable, or we said, or the other people said state stabilizers. Here we will need two sets of measurement, which it is two sets of measurement, which is controlled by UA and UB. Okay, and the measurement, the local measurement, which we denoted by MJ, it is actually a projective measurement. Well, the basis is UJ transform, UJ acting on the EM, okay, or EM transformed by UJ. Okay, we transform the basis with a local unitary and then implement the measurement, such that we can get two different measurement settings. So, and as a whole, we will have different UJA, UJB, such that we will have different measurements. And then this different measurement, we will find the projectors that supports the target state. This S is the supporting set of a measurement output for a target state. What is supporting output? That means that after the UJA, UJB transformation of the target state psi AB, and the supporting output is that the output that which is not zero probability. That means we will have added some possible output on this output, and we just exclude the zero probability output. Okay, this is a supporting set of the measurement outputs, and we just sum up all the projectors on the supporting measurement output, and this will certainly stabilize the target state. Okay, so this is how we construct a stabilizer for the target state in one measurement setting associated with JA, JB. And if we have here is the okay, and if we have a different set of the JA, JB, then these two bases. So here we have J prime and J, and these two bases may have a different they are not, in general, they are not orthogonal to each other. And if the inner product between these two bases is 1 over square root of n, then we call it is mutually unbiased basis. And this mutually unbiased basis is preferable for entanglement detection, for constructing the entanglement witness or to the entanglement value file. And so here is an example to detect the entanglement for a task state psi AB, which is a superposition of a HV plus VH. And this state can be at the same time written as PP minus MM. Okay, and P is plus, M is minus. H is, we use the polarization degree of freedom for polarization of a photon to indicate the qubit. Okay, so H is horizontal, V is vertical polarization. So the first measurement that we want to detect is the at the computational basis, where we just do nothing before the measurement. Okay, before the measurement, do nothing. We just directly measure the state in a computational basis, and we will certainly get the correlation between HV and VH. So you will have half and half, 50% for HV. Here's VH and 50% for HV. Okay, and now if we transform the basis, this is like a quantum proposal story. Alice changed the story. Alice changed the basis to yes plus no, or yes minus no. And now here Alice changed the basis through this kind of Hadamard gate. And at the same time, if Bob also transform to the plus and minus state with this Hadamard gate, then we will have another measurement setting. And in this measurement setting, we also have this perfect correlation, half P and half PP correlation and 50% MM correlation. Okay, so in the computational basis, we will then construct the stable file as VH, a projection on a VH, HV plus VH, another projection on VH. And then the stable file stabilizer on the second measurement will becomes projected onto PP plus projected onto MM. Okay, and VID and VH all stabilize the target state. So now we can sum up all this VID and VH to construct a V entanglement, entanglement verifier. And this entanglement verifier certainly stabilize the target state. And now we can calculate the maximum of this of the maximum value for this stabilizers or this entanglement verifiers, which is equal to half. And then if we get the expectation value of this VEN greater than half, 1/2, then we can certainly conclude that testing state is entangled. So this is how we construct the entanglement file in this bipartite qubit system. So in a quantum, in linear optic networks, we use multi-UL encoding to encode a qubit or encode a qubit. What is a linear optic network is that we construct a very complicated multiphoton interferometers with spin splitters, and we have an input and we have output. Input is here it can be single photon input, it can be also a continuous variable input, and here we just look at single photon input now at the moment, and the output in the output we will measure the photons with photon detectors. Usually it's photon number resolving detectors for multi-photon cases. But in this system, we can use a unitary matrix to describe the transformation of the mode. And here we have a M mode system. And this kind of M mode system, which is a M rail, like the rail of the train. We have a M rail. It's an M rail system, multi-rail system. The inputs, a single photon input, it will be if we go through this interferometer, it will have some probability that detecting certain output. So the transition matrix of this U can be simply described by a matrix, a unitary matrix, and we can also describe in this schematic figure. And how can we construct the so how can we now in this system? How can we construct the mutually unbiased basis or construct complementary measurements to detect entanglement? We will need this Heisenberg field operator to identify the eigensystems. And I think I will skip this part. So you just need to know that there is some operator called Heisenberg field operator. It is actually a generalization of the Hadamard gate in a qubit system, to a higher dimension system, higher dimension qubit system. And this lambda j, we use lambda j to denote this HW Heisenberg field operator, which is a combination of x times z to the power of j. Okay, and the eigenstate of this lambda j operator is mutually unbiased to the computational basis. So therefore, if we can measure, we can implement some measurement in this Heisenberg field operator, then we can implement a complementary measurement which have mutual unbiased basis to each other, which allows us to construct the desired entanglement verifiers to detect entanglement, and the transformation to transform the computational basis to this Heisenberg field eigenbasis is the generalized Hadamard transformation Hj. It is actually a combination of a discrete Fourier transformation times a phase modular V, and Hj, the inverse of Hj is equal to F times V to the power of J. And this Hj, it works like you map the eigenstate of this lambda j into the computational basis. So kind of you want to measure the speed of the rotating handle of your clock, and this Hj will then map the speed to the label of the clock. Okay, so as a result, if we can take, according to all of this observation, now we can construct a state verifier in a complementary measurements. And the first one, the simplest one, is the measurement in the computational basis, and this means we do nothing. And here we have a multi-rail M-rail system, and we have here is an example of a three-party system. We have three parties, and in this system we construct the state verifier VZZZ, and which is just the projection onto the projectors that supporting the target state psi ABC. Okay, we have a target state psi ABC, and we have a testing state rho ABC, and we construct a entanglement verifier or state stabilizer VZZZ, which is just the projectors onto the supporting set for the psi AB, okay, in this measurement. And then we can, then this VZZ certainly stabilize the target state psi ABC. And now we can also construct another V operator, another stabilizer for the target state. In another complementary measurement, use the generalized Hadamard transform. And then we just pick out the supporting output projector on a supporting output in this measurement to construct a stabilizer VJAJBJC for target state psi AB. And then we get this VJAJBJC. Now we can sum up, we take a mixture of this V operator VZZZZ and VJAJBJC, which assigned with a weight, and the sum of the weight is equal to 1. So therefore, it is a convex combination of this V stabilizers to construct an entanglement file. And now, as this entanglement file, if we can find the upper bound for separable biproducible states, and if the expectation value of this V operator exists this biproducible bound, then we can certainly conclude the entanglement. So I will skip the other part and we'll skip the other. So this is the second part. Maybe let me jump to last page. Okay. The second part just tell us about how do we analyze the multiphoton statistic in a linear optic network to get the signature which is similar to the single photon cases. And in the last part, we will have a generation and evaluation of this multipartite entanglement in the system. And I think here is the schematic figure that how we generate multipartite entanglement in the system. Here we will have inputs and use a multimode splitter to distribute this input into different local parties, and in different local parties we will use this Hadamard. We'll use this generalized Hadamard transform to construct the corresponding state verifiers to detect the entanglement. So so here is the stable verifier file constructed in different in a tripartite entangled case. So I think I have to skip off this. And here is an example how we detect the entanglement and the genuine multipartite entanglement. So this is the expectation value of some entanglement verifier, and this line is the boundary for biproducible state. And then you will see if this line exceeds this boundary, then we can detect entanglement in experiment. Okay. So then let me just come to the conclusion. I think I can just conclude with this equation. And so far, I think that in this seminar, the main message is that the detection of the multipartite entanglement experiments for multiphoton boson sampling system, it was quite similar to the detection of a multipartite entanglement in single photon linear optic network system. And the principle is just that we need to find out the verifier, entanglement verifier that stabilize the target state, the target entangled state. And now we need to evaluate this, the expectation value of this entanglement verifier to see if it exceeds the boundary for biproducible state. Of course, this boundary is determined theoretically, and it will give us the signature in the experiment about if the state is entanglement or is a multipartite entanglement or not. So yeah, I think I should, I have to stop here. Right. this already one.
Thank Professor Wu Junyi for giving such an interesting talk. And and since this is an online talk, so the student they just watch the on YouTube, so they cannot ask questions. So
already.
would you please allow me to ask a few questions?
Yes, sir.
And in your conclusion, you said that because you consider the entanglement verifier, but there are many other witness or entanglement formation or many other quantities. The people are talking how to make those entanglement set in more concrete way. And so here you study from the entanglement witness, and starting from that you deliver your whole scheme.
Mm-hmm.
And my question is, what about if other entanglement measures or entanglement stuff? Because as a series, we usually calculate many things. And so we trying to separate those or trying to map the whole state structure in a more concrete way. And so entanglement witness is just one of them, but there are still other quantities. Are those quantities experimentally, they are easy to make some kind of judgment or some measurement to map out those quantities more clearly?
So, entanglement. So there are, some criterion, some entanglement criterion. It can be used to estimate the lower bound on entanglement measure. So even entanglement measure is sometimes you cannot get the exact number in theory.
Yes. Yes.
So even in theory, you even need just approximation or estimation on the lower bound. This is in experiment what you can do. But and this lower bound, for example, if you use this convex roof extension and then use some technique to estimate the lower bound, and this lower bound actually still can be estimated by experiment. And then no matter what lower bound you get, you will still need to construct a kind of witness, right? And some witness is non-linear, some witness is linear, and this the construction of this entanglement detection here is based on linear witness, and of course we can improve this linear witness to nonlinear witness, and the nonlinear witness will get more close to the entanglement measure, to the concrete geometric, because the linear just cuts the point, but nonlinear you can kind of get closer, get this, you can kind of curve this line, and you can have more touching point.
Yes.
And so and different entanglement measure, they have different estimation techniques. They have these different characterization, different nonlinear witness that's corresponding to that. So yeah, and in the point in here that where I use this very quite simple, naive linear witness is that in a multi-photon boson sampling system, it is quite hard to get the element of a density matrix. So I think many nonlinear witness is like you you directly measure some part of the entries of the density matrix. Just pick up some anti-diagonal matrix, anti-diagonal entries of the matrix in the experiment. And then from these entries, you can construct the nonlinear weightiness to determine the lower bound on the entanglement measure. But for this works quite good for single photon material system. But if we have a multi-photon in a boson sampling system, then it is quite hard, even also in theory, to get the single density matrix entry. So therefore, here what I have done is still just with the linear entanglement weightiness.
Okay. Okay, thank you. And so I hope that maybe in the future, next semester or something that you still can come to give a seminar on your skip second part and more elaborate on your third part.
Okay, yeah. Sorry, maybe I didn't control the time quite well.
No. It's quite clear for general introduction. That's good.
Okay.
Mm-hmm.
Yeah.
Okay. So maybe time's up. So we have to finish today's seminar. And so thank Professor Wu Junyi again for his clear and pedagogical talk. Thank you very much.
Yeah, thank you for inviting me.
Uh,
And please take care and stay here.